Welcome everybody. Hope you are having a good time here at KubeCon. And today we are going to share how we built a AI HPC cluster on the top of Kubernetes in public cloud. Uh, so quick introduction. My name is Chandan Avdhut. I'm a production engineer at Meta. And my co-presenter, Kalyan Saladi, he's a software engineer. He couldn't be here in person today. But for his part of the presentation, we have a recording that we are going to play. We both work on different teams, but our team collaborate together to build and operate AI HPC cluster for research in public cloud. So today we'll go over like overview of AI ML training, how it looks like, what are the infrastructure requirements for running AI HPC workloads, running Slurm on Kubernetes, and node lifecycle management, and some of the storage aspects of the cluster. So with that, I'm going to play a recording. So first part of the session is covered by Kalyan. So I'm just going to start the video recording.
Thank you, Chandan. Hello, everyone. My name is Kalyan. I'm a software engineer in research infrastructure team at Meta. Sorry, I couldn't be there in person at KubeCon this year, but I partnered with Chandan to help you understand what ML training and research space looks like and what does it take to build a performant and highly productive research cluster in the cloud using Kubernetes. So let's move on and try to understand what ML training is at a high level. This is an oversimplified picture, but you can imagine a training loop, typically in PyTorch, deployed on a bunch of GPUs, right? Each of these GPUs is operating on training data samples and iteratively computing and refining the weights. This goes on for a while, eventually resulting in a set of weights that would be called a model, right? The model is going to be released for production or for open sourcing, right? To give you what are the examples of models like Llama, Mistral, GPT-4o, you all might be familiar with, right? Before we understand what does it take to build ML research cluster in the cloud, it's very important to understand how does it differ from traditional workloads, right? I'll focus on 3 dimensions here. Number 1, runtime or lifetime of the job, as opposed to web services where the requests take a few milliseconds or hundreds of milliseconds, right? Here the jobs run for anywhere from hours to weeks to months in some cases. That means the time span that you're looking at is really different. The second dimension is job size and semantics. The semantics are really important here. You have this all or nothing semantics. Say you have a 16 GPU job. If any one of the GPUs is unhealthy or is suffering from some sort of infra failure, the entire job is impacted. Even if the other 15 are healthy, you're effectively restarting the job, right? This is quite different from the traditional web services where each node is independent of the other, and if a particular node is unhealthy, you can retry the request on a different node and still satisfy the request, right? As you can see, given the lifetime of the job and the job size semantics, reliability becomes that much more important in the context of training workload infrastructure, right? Yep. So we have a very high level understanding of ML training, right? With that, let's figure out what is an ML research lifecycle, which is actually quite early in the entire ML lifecycle. If you see, these researchers are innovating in the model architecture or the model capabilities, right? Let's go through a typical research lifecycle. Researchers are reading papers, understanding the latest model innovations. They're reproducing the results from open source, or they are starting with a state-of-the-art model that they have and trying to identify future directions. They eventually come up with some proposals, right, based on the directions they identified. The proposals result in they move on to experimentation phase, which may involve ablations, sweeps, hyperparameter sweeps, new model architecture innovations where you need to modify the code and prove that the architecture works. Eventually, when everything settles down, you go into your scale run mode, meaning you are now ready to launch your workload on hundreds or thousands of GPUs based on the model's compute requirements, right? Once this process finishes, the final result is going to be like published model or productionized model or released to open source community, the code and the model, right? That's what we are looking at. If you followed the space, models have been rapidly evolving, getting bigger and more efficient of late. And if you look at this curve, the model complexity in terms of GFLOPS expressed is a really dramatic illustration of the complexity growth, right? We can kind of safely assume that the curve is not going to meaningfully shift downwards, and be prepared to handle the scaling needs of ML training in the future. Okay. Before we figure out how to build a research cluster, we need to understand why researcher experience is paramount to our design, right? As we talked about it, researcher experience in the researcher experience slide, there is a lot of iteration involved, right? Effectively, iteration speed is what is unlocking innovation. If you're able to experiment more and prove or disprove your hypothesis, you're able to move further along in the direction that you want to, that you have identified, right? Researchers, simply stated, researcher taking an idea to experiment should be as fast and as simple as possible. The more the barriers, the slower the innovation, right? The second part of researcher experience I would like to call out is, since this is research and experimentation, there is bound to be failures. Researcher is going to face a ton of failures. And the key aspect here is, can we separate the research failure versus the infra failure, right? And that's one aspect. The second part is, can we give first-class monitoring and node resource metrics so that the researcher is able to track how is my model doing and how am I using the compute and the resources underneath, right? The third aspect of researcher experience is training reliability. The more the interruptions, the more the researcher is wasting time debugging those failures and figuring out, is it a code bug or is it an infra bug? So we have a goal to keep interruptions to a minimum, right? And support long running jobs at massive scale. Okay, we talked about reliability already, but let's really understand why distributed training reliability is such a challenge. In this picture, you're seeing 4 servers with 2 GPUs each running a workload, running a ML training workload, right? Slurm is dispatching these tasks to the workers, to the servers, right? And the workers are pulling training data from the data store, right? There are different training aspects, but one key thing to understand here is that all workers need to be in a consistent and consistent in terms of configuration. If you have divergences among these nodes, you don't have control over the outcomes, right? And the nodes need to be healthy in order for the job to progress, in order for the training to make forward progress. So this is again goes back to the reliability and why reliability is so important. The outer circle that you see is the workers communicating among themselves, which means you need to have reliable compute, storage, and the network. If any of these components are weak or unreliable, your job is getting less productive time, training time on the cluster, and that's really key here. This might be somewhat obvious to most people, but the other non-obvious aspect is the sort of lockstep training approach that is currently in vogue is going to result in load spikes on central components and services in the component. Let me explain what I mean. Say all these, so let's take a multi-thousand GPU job, right? When the job decides to take a checkpoint, there's going to be massive load on the storage servers when the checkpoint is written, right? And then right after the checkpoint is written, you will have near zero activity on the file system. And then back again when it comes to the next checkpoint. There are multiple examples of this load spike nature. So it's very important to design the cluster in a way that can sustain, that can handle these load spikes. One other aspect of reliability is, which we also alluded to in the researcher experience part, is the attribution of failures is critical and it is also a challenge, right? Imagine a multi-week job that's running on 1,000 GPUs. And if your same infra component is failing the job, but we are unable to root cause it, it's going to be really expensive, right? You need to be able to have good observability to enable you to pinpoint what component is producing job symptoms and how you can mitigate or improve, close the gaps. All right. So we have a sort of a picture. We talked about what ML training is, what researcher experience should be. Now let's talk about where did we start before going to the cloud, right? This is the picture that you're seeing is a real cluster that was custom built and launched in 2021-22. And we had thousands of DGX servers with GPUs, with CentOS running on them, and orchestrated by Slurm. Slurm is the scheduler that we used. The cluster had directly managed backend network fabric, multiple petabytes of flash storage, and purpose-built storage to accelerate training, a purpose-built storage service to accelerate training, right? Now, this is awesome. This is direct control that we had, but can we take this, and the challenge is, can we take this and replicate it on the cloud, maybe even do better than physical cluster? To understand what we are talking about, this is what a typical Slurm research cluster looks like from a researcher's point of view. They don't see the rest of the complexity. The researcher is logging on to a bunch of nodes, one of these nodes, and they have access to the control plane, which lets them submit jobs to the cluster. And those jobs are running on the worker nodes, right? And let's take our requirements and let's project it onto the cloud, right? What does an ideal ML research cluster in the cloud? Let's come up with that problem statement. We want the same experience of researchers able to log in, get access to control plane, submit their batch jobs to the queue, and Slurm being their dispatching agent, which distributes the workload onto the compute nodes. Of course, you have the storage, which helps you do the data, load the data training samples and support checkpointing, right? This is what we want. But on the characteristics side, we want near bare metal performance. We don't want to compromise the researcher experience, and we don't want to slow down the research velocity, right? We want to be able to support long-running jobs with heavy data exchange among the workers, right? And demanding data loading requirements with terabytes of data, if not petabytes of data being pulled by the GPUs, right? All this has to be accomplished while keeping things stable and performant. One of fundamental requirements that we lay down for any cluster that we consume, that we operate on, is there is no perfect reliability when it comes to GPUs or these nodes, right? Our job becomes, can we find the bad nodes fast and isolate them and shield the workload from the infra failures? And this is a goal that we want to accomplish even on the cloud. And you will see later in the presentation as to how we accomplish that. Okay, now that I have laid down the case and we have a problem statement in front of us, I'm going to hand it over to Chandan to see how we solved these problems and built multiple research clusters in the cloud leveraging Kubernetes. Over to you, Chandan.
Okay, so we just saw like how we wanted to have like research cluster built in the cloud, so in the public cloud. So when we started, we did not like started using Kubernetes at the from the start. So we use something like this. So we have a meta instance. So in Meta we have something called meta instance, which is just a machine image that we use across the public cloud providers. So we take the cloud provider based images, host images, and then we put our own layer on top of it. So here in the yellow, you can see the containerized meta instance layer. So pretty much everything runs as a container, everything that we manage. But on the top of that, uh, our the different teams at Meta can put their own applications and run it on the public cloud. So in this case, on the CPU nodes, typically we run the control plane components. Those are easy to containerize and run it, so we already have those containerized. But the Slurm component that runs on the GPU node and runs actual workloads, that was not containerized, just because it handles a lot of like resource allocation, C group manipulation, and also it needs bare metal access or direct access to the host to control the resources and allocate it to the jobs. So so this was our first implementation. At the time, the footprint was not that big in the public cloud, but slowly we started growing. There were like multiple clusters. We also started growing across multiple cloud providers as well. So this was clearly not the solution that that will scale for the future requirements. So we knew like we needed a better container orchestration mechanism, and Kubernetes was obvious choice because of being industry standard and vast availability across multiple cloud providers. So we thought like if we change the architecture, we will do something like this. So wherein we'll run everything as a Kubernetes pod, all the control plane components, all the infrastructure components required for logging and metrics, etc. And then we can just leave Slurm as it is running on the host, so that we don't have to deal with the complexity of resource allocation at the SUMD level and get involved into process of researchers submitting a job and then that job getting allocated on the Kubernetes on the GPU node. But we ended up implementing something like this. So now cluster is divided into two different parts. On the right-hand side, typically we run things like ingress and egress gateways on top of Kubernetes. There are a few other infrastructure components that run there that are common, that are reusable across various clusters. And then there is the left-hand side where we actually run the GPU cluster and all the components that are required to run the workflow, including the login environment, control plane components, and all the components that we need for need to get the telemetry out of the cluster. So reason for doing this split was the right-hand side pretty much like stays the same. We can reuse it across multiple cloud providers. We don't have to customize it at all. On the left-hand side, because we are running on Kubernetes now, we can take that and run it across multiple cloud providers, but we still have to do some customization based on the like cloud provider or specific needs of the cluster, specific hardware, etc. So only thing we need in between is the L3 connectivity, so that like they are connected over the network, and that's about it. So as we moved on to Kubernetes, and like it kind of like made our life easier as an infrastructure team to manage infrastructure across various cloud providers. We did not want, we wanted to make sure the researchers, either we provide a better experience for the researchers, or at least we match it to what was it before we moved to Kubernetes. So typically when the researchers log in, they just run Slurm commands to run their workflows, and so we wanted to keep that same. So because on the Kubernetes now, you have to run like Helm, kubectl, things like that to interact with the Kubernetes cluster. We did not want it to have researchers learn all that or change their workflows across various environments So we wanted to completely avoid that. So to do that, what we did is we came up with a custom CLI that researchers use to log in into the cluster. So that's custom CLI. In the back end, it just creates a small Helm release custom resource definition. And then we have a Flux Helm controller that is running inside the cluster. So whenever researchers log in, that Helm release object is created, and then dynamically a login pod is created for them. And when that pod is up and running, SSH session is launched, and researchers get into the login environment, and they can, from there on, they can just run their normal workflow. They don't even realize they're inside the Kubernetes cluster. They don't have to run anything. They don't have to learn anything about Kubernetes. So So we also run a Kyverno admission controller. So that is a webhook that you can use. So the admission controller makes sure the Helm release is created as we expected it to be. So for example, if I go and start customizing it to get elevated privileges inside the cluster, it won't allow that. And also, it won't allow me to create a login pod with some other user's name, things like that. So if it validates the policy, it will reject that object, and it will not let you log in into the environment. So with this now, let's compare it to how it was before. So before, we had virtual machines that were shared between the various users, and now they get dedicated pod with the dedicated resource allocation. So now we have better security posture, and also it avoids problems like noisy neighbor. So at the end, we ended up giving them a better experience. Infrastructure component management also changed a lot. It became a lot easier. So now you can see here, we already talked about the Slurm. So we run few more things on the cluster as a Kubernetes daemon set or deployments. As I mentioned earlier, we typically just use the cloud provider provided host images, and we don't like to maintain any customization or have to deal with any customization at the host level. But we couldn't really avoid it entirely. So we had to do certain things. For example, in the LO layer there, you can see sysctl daemon set that runs across the cluster, configures the kernel parameters that are required to run our workloads. It also shows the auto mount daemon set that mounts the NFS volumes across the host, providing the consistent access to the file systems. We'll see a little bit more about the auto mount daemon set later in the presentation. We also run various telemetry components, combination of open source, vendor provided, and custom built. So as Kalyan mentioned, it was important to have a very strong observability story, so that if something fails, we can easily triage why it failed, whether it is an application problem or infra problem, and if it is infra problem, how quickly we can solve it. So we have some custom built components such as some job metrics, core dumper, which takes the core dump of whenever processes terminate unexpectedly. We also have few components that are custom Kubernetes controller. So in this example here, I have added user identity and service identity controller, and there is also cert manager. Cert manager is an open source tool for managing certs on Kubernetes. In our case, we use X509 based certs which are signed by private CA, and to be able to do that, and then we have our own policies that apply when when the user requests a cert. So with the custom controllers now, we can integrate with our own tooling. So utilizing open source tooling with some custom layer on top of that to be able to integrate with our own infrastructure components. There are a bunch of other things that run as infrastructure components, and now earlier, pretty much our team used to manage that, working with other teams. Now it become a little bit more. It's become more independent. We can just give them the namespace. They can run their stuff, and we don't have to get in between. They can automate using our Helm automation tooling, deployment of whatever components that need to be run on the cluster. So as Kalyan mentioned earlier, it was important for us to make sure nodes are consistent. So let's say if researchers submit a job across like 400 nodes, all those nodes should have the consistent configuration and consistent image versions, etc. So to be able to do that, what we have is our everything is handled by our Helm deployment automation. So whenever there is a change in the Helm chart or image that gets applied on Kubernetes, and the custom controller running on the Kubernetes, first thing it does, it starts a rolling update on the Slurm nodes, and it updates it drains all the nodes in the cluster. So at that point, Slurm makes sure those nodes don't get any new jobs allocated, and it lets it finish existing jobs that are running on the node. So once the node finishes the existing job, it, it it goes into the drain state, and then the Kubernetes controller then replaces the Slurm pod with the new version, and then undrains them. So now that node becomes available again back in the cluster for to pick up the next workload. We run a few telemetry health checks that run in the Kubernetes control plane, as well as on the Slurm, to be able to detect faulty nodes, and then those nodes are kind of like tracked, and then our support team triages it, and in some cases we have to take it back to the cloud provider uh, to get it fixed or replaced. So for the storage, uh, because AI HPC workloads are like data intensive, we needed to make sure we provide menu of storage options, starting from simple POSIX storage to AI accelerated object storage. So for non-POSIX storage, such as object store, we did not have to do any changes because we moved to Kubernetes, because pretty much just depends on the client, and they just make the same API call they used to make before. But for NFS, because if we look at the Kubernetes and how Kubernetes handles like volume mounts using CI/CD drivers, persistent volume claims, and volume mounts, etc. Anytime you want to mount a new volume, you need a pod restart. So that is not possible in our case, because we don't want to disturb AI workloads that are running there. We wanted to have a way where we can, without any disruptions, introduce new file systems or take away existing file systems when they are not needed. So we ended up implementing something like this. So as I talked about auto-mount demonstrate a little bit earlier, so auto-mount demonstrate runs across the cluster on every single node, and it makes sure it mounts NFS volumes. NFS file systems. So those file systems are categorized into various categories, such as checkpoints, dataset, infra, and those categories are parent directories on the host. And inside that parent directories, those gets mounted, and then those parent directories are bind mounted inside the slumd and login pod, so that whenever new file systems are added, nothing changes for slumd and login pod, but those file systems become available for the workloads. So to conclude, so from on-premises to public cloud across multiple cloud providers was made possible by moving to Kubernetes. As we kind of like iterated over the iteration speed. So now because we are on Kubernetes, various teams can handle their components independently. We are able to we are able to deliver things faster in the cloud, making more services, new features available faster, unlocking the innovation. And we are also did not have to sacrifice on research experience. That was very, very important for us. From performance and reliability sides, we did not have to, so we kind of like met the requirement that was set forth, even though we moved on Kubernetes. Or in some cases, we have better observability story, because we are able to utilize tooling from cloud providers, as well as open source, as well as custom build. Running HPC on Kubernetes has challenges at scale, but most of those we found were addressable. But still, it's not like pain-free environment. So there are still some scaling issues that you will run into. Kubernetes ecosystem allows us to move fast across multiple providers. Cloud providers is just obvious, like it just vastly supported industry standards, so it's much easier for easier to adopt and reiterate on. Okay, sorry. Okay, so that brings us to the end of the presentation. I just wanted to also thank the open source community for making all these various components available that made us possible to move to Kubernetes and in very short period of time. With that, that concludes the session today. So with that, I can take some questions. I'll be also available here or in the lobby later if you have questions as well.
Thank you very much for an amazing talk. I have a couple of questions about reliability for the cloud, public cloud solution you presented. The first one is about how do you distinguish between workload level issues, which always happen at scale, and the infra level issues. And the second is when you exclude certain nodes from the cluster because of the failures, do you over-provision on your side to account for them, or do you expect your cloud provider to compensate for this cost somehow?
Yeah, so regarding the first question, so yeah, it can be tricky, and we might not always get it right away, but we have observability story built in to kind of to help, and we are still working on making it better. So for one instance, I can maybe give you an example. So in some cases, what happens is in the public cloud, we found a problem with the node, we send it back to the cloud provider, it comes back, they don't find any issues with it. It comes back to the cluster. Again, that node kind of keeps failing. So we kind of track failures on the particular node across various jobs and kind of try and find, okay, so this is a bad node that caused X number of failures in last 30 days. So kind of keeping the bad actors away is kind of approach we have been implementing. One more tricky thing in the public cloud is the same hardware can come back as a different host. So we are also currently looking into better ways to track that using GPU IDs and serial IDs, and so that okay, we don't depend on the actual physical location of the host or actual name of the host, but we can really track down by the GPU IDs and things like that.
I have a question about your V2 or V3. I don't remember about your Slurm D. How do you deploy that one? You deploy it in the bare metal environment? It seems to me.
Yeah, so it was not clear, entirely a bare metal environment. So it was more on something like AWS EC2. So it has a thin virtualization layer on top of it. So, but we just run.
But your other components is actually part of the container, part of the Kubernetes, right?
Yeah.
But this one is separate.
Yeah, so it just runs on the OS, like a systemd unit.
But when they launch job, what kind of when we finally launch the job to the working node, what does it look like?
Yeah, so in the Slurm, pretty much in the both the environments, when somebody submits a job, they log into the Slurm and they submit the job, and then the Slurm D kind of spins up the task process on the worker node, and that executes the actual workload. So no matter you are running inside the pod or you are running as a process on the host, that process doesn't change much.
And then also about the deployment, in that way you still use Ceph and separate deployment on this node only?
Yeah, so in new model we don't use Chef. We just run everything as a Kubernetes daemon set because we do only small things on the host level. We don't really need a config management and have to deal with differences between various cloud providers, different versions of kernel and things like that.
Okay, thank you.
Hi, I have just one question. Have you considered some open source Kubernetes operator which managed Slurm inside of Kubernetes? for instance, operator or something like that?
Yes, we are reevaluating that as well. So yeah, in near future, we will pivot on that, I think. But yeah, that's something we have been like discussing internally.
Hi, great talk. So I mean, like when you have these long-running jobs and you have to do system-level updates, right? There might be a period where you have to wait for that job to finish before you get the feedback. How do you handle that portion of it? Yeah.
Yes, so on the Kubernetes, because um, now Slumd runs as a as a pod. So let's say if you want to do a security patch on the host, that doesn't need a restart. So you can still do it without affecting the Slum, because Slumd runs in its own namespace, and it doesn't affect it. So that's why I have like everything running alongside of like Slumd pods on that particular host. They can continue to update things, but workload running inside the Slumd pod doesn't see those changes. So it still see the whatever is there on the Slumd. Some things can be tricky, so we have to avoid, for example, like upgrading or changing kernel parameters or stuff like that, or applying a patch. So, but overall, like the things we do normally, such as, for example, hey, we run let's say a metric agent that needs update. We can update stuff like that without having to worry about affecting the workload that runs inside the Slumd pod.
Thanks.
Hey, thanks for the talk. It was really nice. And yeah, I just had a few questions. So number one, I think you said focusing on the researcher experience was paramount. And I noticed you said you created like a fake CLI, in a sense, to help do that. So why did you insist on continuing to use Slurm, shall we say, if you were kind of able to interject in that point and create CLIs in the middle?
Yeah, so question is like why we insisted to use Slurm and why not Kubernetes?
Yeah, so for example, today in this week I've seen sorts of things about training pipelines, Kubeflow pipelines and other things like that.
Yeah.
So, why not go that approach and create things in the CLI to...
Yes, so I think Slurm is like very widely used tool for doing AI research, AI HPC kind of like research, and at least in the near term, we did not had plans to like change that. And then pretty much like a lot of people working in academic research, they typically have a lot of experience working with Slurm, and it also provides way better controls for running long-running bad jobs. So that is something that we did not want it to change. But what you're saying is also like we have been like considering. So we might end up like having another a controller that runs on Kubernetes, but we can keep Slurm for people who are comfortable with using Slurm. But there are certain users they want to kind of like use Kubernetes or some other Kubernetes way of doing things basically. So in future we might end up doing both.
Nice, yeah, I can totally understand the feeling of sticking to Slurm to, kind of get that researcher's buy-in. The second question is actually very related to what you were saying at the end. Would you be able to make this work for a combination of on-prem clusters and public cloud? And I assume that, helps the company stay quite agile as well.
Yeah, so for internal, like we have very mature tooling for internal, like handling internal, like whatever runs in our data centers, we already have like automation, we have like, so we don't need to like do much customization there. But in the public cloud, what happens is because we are kind of like limited by what public cloud has to provide, and then also kind of like implement something hybrid that works with our internal tooling. So that's why like Kubernetes helps there. But for the like private clusters, we already have a good tooling that integrates well with our own infra. So not necessarily we have to customize that.
Yeah, fair enough. So what I mean is having a common interface that would be the same for the private cloud or the public cloud. Has that ever been considered? Not really, is it?
No, not really, yeah.
Cool.
Because like there are various groups, various like, it's a little bit complex. Yeah, but because like, yeah, the training workflows are different. There are different requirements and stuff like that.
That's perfectly fine. Thank you so much. Pleasure.
Thank you. So thank you everyone for joining today.